Good morning, ladies and gentlemen. Good morning. It's a pleasure to see you again. We go on with our course of advanced quantum mechanics. Now we got to lecture 2, which has a bit special status. All right? From one point of view, it's the most important lecture in this course. It's about identical particles, and it outlines what is the problem. And it gives an overview. We will learn why particles are fields and field subparticles, very important discovery of 20th century. All that we do to come to a sort of dead end. After we figure out what is the problem, what we need to describe, it appears that the problem is rather straightforward, but complex to do it with your hands. All right? We come to this in the end of lecture when we go to Fock space. What to do? One needs to switch gears. One needs to use different methods. Methods of second quantization, creation and annihilation operators. And that we will study next week, lecture number 3. So today is identical particles, formulating the problem, kind of clearing it up, but there are yet no methods, right? The methods will be introduced in lecture 3. That's why, because I get questions from time to time. The first package of homework will be released after lecture 3. Don't check it before that, because formally you cannot do homework before I told you something about second quantization, lecture number 3. Not yet, not today, but it will come. Fine. What will be concrete topics, how we start and where we go? We will write string equation. We know what string equation is, but we will write it for n particles, for a big number of particles. Good. And we kind of almost immediately specify to identical particles. And that brings us to permutation symmetry, because you can permute identical particles without changing anything. All right. We need to learn a bit about symmetries in quantum mechanics in general. It doesn't do much pain, don't worry. And after that, we can come to very important things. Symmetry postulate. Symmetry postulate is something which you know. I'm sure that at least in TV series, you have heard about bosons and fermions. Perhaps you even know what is the difference. Now we kind of lay a scientific basis for this concept. Symmetry postulate. All right, and that will shortly bring us to quantum fields. We understand how and why it leads us to this idea of quantum fields. After that, I'm afraid it will be a little boring, because symmetry postulate will tell us that we have to symmetrize and anti-symmetrize large wave functions, and it's a bit a tedious task. I will do this. There's nothing wrong with this, but well, it might look a bit boring. Final goal of this lecture is to come to Fock space. Fock space, it's a name, Fock. It has a special, very special for us. It contains only quantum states which are allowed by symmetry postulate. It doesn't contain anything extra. It's just a space to work on, but again, it will be clear from all these calculations that it's difficult, if ever possible, to work in Fock space with usual methods, which we study in usual quantum mechanics. We need something extra, and again, I'm telling that for fifth time, perhaps. That will be lecture number 3. Good, let me start. So, showing the equation for n particles. First of all, and perhaps it does not clear from very beginning, but it is important to note that for n particles, we don't have n wave functions. We have same one wave function to describe all the particles, all the quantum states. As such, it has to incorporate information about the particles. That's why it has an awful plenty of arguments. So, 3-dimensional vector per each particle. Look, I will use this notation rather frequently. If I have a row of such numbers, vectors, whatever, I put it into curly brackets. Good. 10 particles, 30 arguments. If you want to describe quantum state of this room, well, it would come for many, many zillions of arguments. That's it. But wave function would be still a single wave function. Good. We understood how wave function would look like. Let us arrange the Hamiltonian. First of all, we need the usual Hamiltonian, which is also valid for a single particle. We remember that there is a kinetic energy and there's potential energy. At the moment, index I, my distinguished particles. So all these particles might have different mass and might feel different potential energies. All right, let us see if you understand what we need to do to make it identical at this Hamiltonian. Right, I can do it on spot. I made the mass the same for all particles. And they feel the same potential energy. Good, but it's still a sum of Hamiltonians for each particle. Oh, why would it be sum, right? Like energy, if particles do not interact, the energy of the system of particles is a sum of energies. That's why it's natural that their Hamiltonians also sum up. Each Hamiltonian depends on the coordinate of corresponding particle. Don't forget about this. This index would not disappear. Okay? Right. Next to it, there is interaction. Right? How do we add interaction in the Hamiltonian? It's an energy, right? It's an energy which depends on the coordinates of two particles. I could sketch a Coulomb law, for instance, as an example. Then instead of this VI, I would put, oh, never remember that stuff, just like this, R1 minus R2 modulus. That's Coulomb law, if I remember correctly. Interaction of particles with the same charge. But whatever, in general, just a function of two particle coordinates. Again, what do we do to make it identical? Oh, we just skip indices. So there will be the same function, which depends on each pair of coordinates. And now I have to sum up over all pairs of coordinates because each pair of particles interact. Well, I could go further. I could think of interaction which involves three particles. It is a term which depends on coordinates of three particles. Again, if I assume that the particles are identical, what I have to do or just to write this indices, which means that interaction of any three particles is the same function of coordinates. Good, we've done it. I've sketched the most general Hamiltonian for n particles. That's too complex to solve, of course. And most of the lecture, I will skip interaction. But even that, it appears not that simple. Still requires some work. Good. Schrödinger equation for n particles, which can be made identical by assigning the same masses, the same interactions, the same potential energies. Right. I didn't put it on transparency explicitly. Let me tell it explicitly. If Hamiltonian, if the particles are identical in this Hamiltonian, the Hamiltonian is symmetric. There is an operation which can be done and which does not change the Hamiltonian. In our case, this operation is permutation of particles. Particle 1 goes to the place of particle 2, while particle 2 goes to the place of particle 1. And one can arrange larger permutations involving more particles. Whatever the permutation, the Hamiltonian will remain the same. Hamiltonian is said to be symmetric with respect to this transformation. What I wanted to tell you now is to tell you about something which you know, but perhaps never ponder, never got it explained properly. It is about general concept of symmetry in quantum mechanics. And bottom line, I would put it into beginning. It's perhaps a little bit counterintuitive, but it's the fact. If Hamiltonian is symmetric, one could easily accept that its solutions, its eigenvalues are symmetric. But it is true, there are symmetric solutions, there are symmetric states. But there is a lot of solutions which are not symmetric. So how to understand it? how to swallow this. Something that you know, hard-wall potential particle in a box. That is ground state. Oops. That's symmetric. Next state looks like this. It's anti-symmetric. It flips sign if you apply symmetry. What is symmetry here? It is reflection with respect to this plane. And then we go again and again as a symmetric, asymmetric, symmetric, and asymmetric state, so on. Right. So all solutions of this Hamiltonian and any Hamiltonian with mirror symmetry have this label. They are either symmetric or anti-symmetric. And that label has a strange mathematical name. That label is called irreducible representation of the symmetry group. Mirror symmetry at simple group, it has only one element. So there is a simple set of irreducible representations, either symmetric or anti-symmetric. Right. Let us look at something which you know, but which is way more complex. Let us recall whatever what we know about atoms. Let us recall about hydrogen atom, for instance, when we have an electron, or perhaps many electrons, it is spherically symmetric potential. Spherically symmetric potential of the nucleus. Fine. I bet you remember what do we have. Each state in this spherically symmetric potential has a label, which is usually called, tell me. Orbital is a good word. What is the quantity associated with the orbital? Angular momentum, precisely. Usually you learn about this about quantization of angular momentum in spherically symmetric case. And indeed, it gives rise to classification of orbitals. There are s orbitals, and they're completely symmetric with respect to rotations, any rotations. There are p orbitals, 3 of them. So there's a degenerate irreducible representations. They correspond to vector, right? They're very distinct from S. Very good. Then, you know, there are d orbitals, and they are more like tensors, whatever, more and more complex, and that set never ends. So what does it, how can I formulate in mathematical terms? There is a symmetry group of all rotations. It has irreducible representations given by this row, S, P, D, whatever. They correspond to quantized angular momentum, and there is also degeneracy associated with these levels. So that's how symmetry appears, manifests itself in quantum mechanics in general. Group irreducible representations, and whatever crazy wave functions do you have, they obey this corresponding irreducible representation. All right? Yes?
For me, it's not very clear what an irreducible representation actually is. Yeah. What do you mean by that?
Yeah, in 2 weeks, when we go through group theory, one can get it. Was anybody so unhappy as to learn group theory in this audience? You. Okay, you just ask these guys. Right, so now we have minor of whatever, mathematics and physics, or some people are exposed to this. Group theory, which used to be one of the powerful tools of quantum mechanics, because it can tell you about something, about wave function without computing this. Physicists like it. Fine, symmetry, so let's get to symmetry. We have in the hand, we have permutation symmetry. What does it mean? We can introduce operators of permutation involving two particles with indices n and m. What's important is that the squared of this operator is 1. Indeed, if we make a commutation twice, we just get to the same state. All right. Let me give the simplest example, two particles with wave function like this. We apply this permutation, what we get? We get wave function with exchanged arguments. All right, one can do it for 3 particles. For them, that's just 2 arguments got exchanged, corresponding to particles 1 and 2. Right. We can figure out very quickly what are simple irreducible representations of this group. First representation, and it always occurs, is a symmetric one. You do this to wave function, it does not change absolutely. Second possibility, you do it to wave function and it flips the sign. Right? Why does it flip the sign? What its minus? If I apply it twice, I would have to get 1 anyhow. So that means that, minus 1 squared is 1. That's good, that's simple, that's something which you perhaps have learned. I don't know what was either quantum mechanics or perhaps statistics, or I don't know what people usually know about fermions and bosons, symmetry and asymmetry with respect to antisymmetry with respect to permutations. The point is that it's not all. If I look at this permutation group, very much in brackets, mathematicians told me that permutation group is a mother of all groups. So each group can be represented as a subset of a permutation group for sufficiently big number of permuting particles, right? And it implies that there are more complex, multidimensional, irreducible representations. Which would involve many wave functions. Okay, and if they would actually occur in nature, I would have a terrible problem of giving this course, and you all would have a terrible problem to understand quantum mechanics. For some reasons, and I will try to outline, if not the reason, but at least the motivation, these representations of multidimensional representations do not occur in nature. That's how we come to symmetry postulate, which again, I believe you know in some point, in some way. Identical particles can only come in two sorts. They're either bosons, and that means that their wave function is completely symmetric with respect to all permutations, or fermions. And in this case, wave function is anti-symmetric with respect to each permutation of each pair of particles. And as I promised, there are all possibilities which occur in nature. There are no complex irreducible representation, which means the following. I wrote Schrödinger equation for you. It has a plenty of solutions. But most of these solutions are forbidden by symmetry postulate. Right? So one can wonder how symmetry postulate comes about. There are tricky ways to figure it out through relativity theory. Actually, I was never sure that it's a good foolproof, but people can argue about this. But for me personally, it is easier to regard it as an experimental fact. It just happens so, and one can figure out this from measurements, from very simple measurements related to, for instance, thermodynamics of ideal gas. Perhaps, I don't know how much thermodynamics you took. There was yet in 19th century Gibbs paradox. When you kind of mix two gases, the entropy does not change. Although each molecule has a bigger volume to pass. Right? That has everything to do with identical particles. So one can say that, just measuring entropy of ideal gas provides you experimental verification of symmetry postulate. So let us regard it as an experimental fact, something which is given for us. And let us look at the consequences. What we have done, for instance, with Schrödinger equation, we can easily make it identical just by scraping some indices. But if you recall symmetry postulate, well, it looks like we have to do something else, which means that identical particles in quantum mechanics are kind of more identical than in classical mechanics. As they say, it's undistinguishable. I would prefer to call it elimination of cheating opportunities. So at this point, I usually do demonstration. I have also care about Zoom participants, but let's see how can I do this. These two pieces of chalk kind of look very much the same. Let us call them identical particles. So if I look at it, I could not distinguish which piece of chalk is on the left and which is on the right. Okay, so there's one state. This piece is on the left, this piece on the right. Yeah, some participant, this piece on the left, this piece is on the right. Now I do exchange. It looks different state. Okay, you have seen that I've made a change. You can tell, yeah, Yuli, you made a different state for us. Now suppose I kind of order you to close your eyes. Close your eyes. Did I exchange the particles? You cannot say because your eyes were closed, you did not observe the situation, but the state looks the same. So I could cheat you infinite number of times, or whatever, somebody in the universe could cheat you infinite number of times. And there's a very elegant way to organize the world in such a way that this cheating is not possible. Let me write a couple of formulas for this. So eventually we've been dealing with two states. First piece of chalk was on the left, second on the right. After transformation, it will go to a different state. Which one? So now second is on the right. So first is on the right, second on the left. This state, distinct one. Okay, but you cannot distinguish between these two states unless you follow my hands. Okay. So how to make this the situation to eliminate the cheating? One could say that the only wave function which can occur is a symmetric superposition of these two. Symmetric superposition, I have to divide it by square root of 2. Why? Very good. Then it's normalized properly. Good. So if I have this state, what will happen if I exchange the particles? Nothing. I'll be in the same state. So I won't be able to cheat you with this. Okay, that is for bosons. For fermions, we have minus sign here. But okay, that means that wave function changes sign, but changing sign or any sign in any phase factor to wave function actually does nothing, does not change any observable. So for practical purposes, it is still the same state. Fine. That's what we learn, and this is kind of, I hope, easy to remember. So all these terms and bosons exist in order to simplify our world, in order to make kind of system of states simpler and exclude existence of states which we cannot distinguish. That would be a little disaster. Fine. Now I'm getting to the fields. Actually, symmetry postulate was difficult to accept, but once you accept this, whatever as an experimental fact, the concept of quantum fields is just one step away. To understand this, let us ponder about the following situation. Here in Delft, experimentalists did some nano-experiment. They've caught an electron and put it in the box called quantum dot, whatever. At the same time, even without exchanging information, our colleagues in Japan did the same. In 12,000 kilometers from here, they've caught an electron in a quantum dot. And what symmetry postulate tells us? The wave function of these two electrons is anti-symmetric. How come? The guys don't know about each other. They're separated by a distance. There is information barrier between them. Nevertheless, the wave function is anti-symmetric. Locality is very important principle in common life, everyday life. You know that your kind of prosperity does not depend on something which occurs in the war, which occurs 10,000 kilometers away, whatever, even from your neighbors, which are kilometers away, all right? Locality principle, also very important in physics. Events, objects interact only if separated sufficiently by sufficiently short distance in space and time. This locality is bluntly violated by symmetry postulate. So locality for particles appears to be destroyed. What is the way out? The way out is logical. There's something which is the same in Japan and in the Netherlands, and which provides these electrons. In more mathematical language, there is electronic field. The property of vacuum to have the property of vacuum is a potential to create excitations, namely electron excitations. So both electrons in Japan and in the Netherlands just originate from the same field. That's why the wave functions are anti-symmetric. That's why there are no identical particles, but there are quantum fields. And field is the same throughout the galaxy. It just whatever some property of vacuum of the ground states and property which can give you excitations, particle excitations. All right, so I told you an important piece of information, whatever philosophical it might sound. For me, it was the greatest discovery of 20th century. Quantum fields, just derived from symmetry postulate. Okay, that time physics has been developing very fast, so people kind of made this discovery, they didn't ponder about this, they just went on. But yeah, if we look at it from the time distance of whatever, 70, approximately 70, 80 years, then you see how great was that and how simple it was. Good, quantum fields. Any questions about this? Any thoughts? Let me tell you something about which I'm not going to tell you anything. The kind of direct consequence of these ideas, this field theory gives you a straight way what to look at, what to investigate, mostly theoretically, what to develop. That's how people came to modern relativistic quantum field theory, which also incorporates relativity, the fundamental property of our space-time, and that relativistic quantum field theory has many applications. I have mentioned already one. It actually explains relation between spin and statistics, or everything which has half integer spin is a fermion. Everything which has integer spin, including zero, is a boson. Right. It explains quite a bit about strange zoology of elementary particles. I mean, if I would organize the world, well, I'm a rather boring person, as you could see. I would just make like 2, 3, at maximum 5 elementary particles. But eventually, if you include all resonances, there are several hundreds of them. So thorough application of this relativistic quantum field theory allows to tell a lot about properties of these elementary particles. Good. Also, this set of ideas, which has been developed, gave non-trivial relations between these fields and geometry of space, time, what is now called strings or deep brains. There are very strange, crazy ideas. I would say it's really celebration of what intellectual power of humankind can achieve. Why didn't I tell you about this? Because it is still very far from engineering level. It's very far from engineering. So let's forget about this, at least for a couple of generations. Perhaps when you come to my place, you will tell something more about this subject, about string theory, about mysterious dimension of 23, whatever. I'm not going to tell about this because, yes, it is still rather unpractical. Good. But if you want to get a good job in a bank or something, you certainly do this relativistic quantum field theory. It's the most direct career path. Good. Any questions? Because I'm slowly switching to rather. Oh, I have a bright idea. Why don't we have a break? 8 minutes break. Morning. Sir, we've been learning about fancy things. Now I have to switch to rather dull job. Huh? He doesn't want to switch to dull job. Yeah, now we do it. We have to sort out the solutions of Schrödinger equation I wrote. We cannot do it with interaction, we do it without interaction. Then we can get everything on row. And now we understood that many solutions eventually don't belong to here, do not satisfy the symmetry potential. That's why one has to get rid of them, right? And we will figure out how to make only correct one's good solutions. Right. Good, no interaction. Then the whole Hamiltonian is just big sum of these terms. To start with, let's take it and let's find all possible wave functions for a single particle. Yeah, just took one piece and I got a series of eigenfunctions. N here numbers the levels in this single particle Hamiltonian. We see already that all these levels are available for all particles. Each particle, first, second, third, can go to the same energy levels, right? So let us see. With this, we can figure out what is a general solution of Schrödinger equation. It is a direct product of these eigenfunctions. It's good with that we don't have interaction, otherwise it won't be direct product. Otherwise these terms will be mixed. But without interaction, it's really so. So you've got such a large wave function which presents one of the solutions of the Schrödinger equation, and all solutions can be presented in such a way. That's why it's general, right? So what I have here, I have a large product of wave functions for particles, first, second, third, and so on, till particle n. And each particle goes to its own level. And the number, the level where it goes, I kind of call with this strange index I of whatever n. So n's particle goes to level with number I n. Fine. So it is looks plasmy. It's made of big number of particles, right? But in principle, it's straightforward. Just each particle, for each particle, you choose which level does it go. And that choice, for all particles, row of choices, gives you wave function. Right. Let me assume at the moment that all these states are available. I told you that they do not exist in nature, but let us assume for a while. In fact, I forgot to tell you about it is completely legal and even straightforward. Imagine a world where symmetry principle doesn't hold. And all particles are different. One can make quantum mechanics of this world in the same way, very logical way. It wouldn't just describe the world we are in, where symmetry postulate exists. Okay, so we assume that all these solutions can be realized, and we count the generosity, namely how many states have the same energy. Good. Fortunately, we can count these energies. Very simple. We just add corresponding energies. Very good, sir. What I do here? Summation over particles, index I. Summation over energies of corresponding levels. Now let me rewrite this sum. And it's important for further applications. Let me rewrite the sum. So instead of summing over the particles, I will sum over the levels. That's logical because each level, now I label those with K, each level has the same energy. And what I have here is the number of particles in this particular level. So completely identical sums. I just redistribute the particles in a different way. N of K, number of particles in the level K. Now what I want to figure out now, in how many ways I can arrange a state with precisely same NK. It's a lot. Right, so what do I have? Let me draw it. I have boxes. Labeled by K. Levels. And I have balls, you know, like in lottery. And I put balls into boxes in such a way that there's NK balls in each box. And I have to figure out how many ways are there to do this. Okay, let me start with the first box. I need to put N1 balls, taking it from the total number of particles I have. The number of ways to do this is given by this combination of factorials. Okay, I'm done with the first box. I go with the second box. I have less balls to start with because I have already used N1 boxes. And I have to accommodate to put N2 particles to the second box. That is the corresponding factorial. The third box, fourth box, fifth box, and so on. Fine. What do I not write a way that these factors cancel each other? Look, oops. The same would occur for the second and all other brackets. So it is collected to this number. I have factorials of full number of particles divided by product of factorials of number of particles in each box. And it's awful plenty, even for moderately small n's. So what does it mean? If we seriously look at all solutions of the Schrödinger equation, we have gigantic degeneracy for energy levels in this equation. But we know that it's not true, that wave functions cannot be arbitrary, cannot be, not all the functions which I wrote satisfy symmetry principle. So I've got some job to do to reveal what are good wave functions. Right. So first, symmetric, it doesn't differ from antisymmetric very much, but still distinct process. So to start with, we fix occupation numbers. Right? We know that all states with the same occupation numbers have the same energy, right? So we are going to lift the degeneracy of the state. Right? And we have many wave functions which differ by permutation of particles. And what we do is rather plain. We just sum them up, all possible permutations. You sum them up, and there is a coefficient which still has to be calculated from normalization. Let me just do it for two particles, right? For two particles in the same level, we have F1, R1, let us see, 2. So one particle in level 1, one particle in level 2. That's one possible wave function. There is alternative wave function which I obtained by exchange. Yes. R1. So what do I have to do? I have to sum them up. In this way, I got symmetric wave function, and it's a good one. It satisfies symmetry postulate. Good. What I wrote in this transparency is that one can do it for any number of particles, summing up overall permutations. Good. All right. So I will replace this plenty of this of the wave function just with single function. A little bit of a problem that it consists of really exponentially big number of terms. That's what makes this calculation pretty unpractical. All right, let us calculate this normalization factor. Okay, this new function must be normalized to 1. One can write it like this. It's a sum over permutations, and one has to take into account only terms in the sum where permutations are the same. All right. All other states are orthogonal. Good. So eventually this calculation gives us number of permutations times c squared. But we have already computed the number of possible permutations when we put particles into boxes, right? So we just pick up this answer. Here it is. Very good. The job is done. we know the formal answer. Right, if you still don't appreciate how tedious is this, just take paper, pen, and do it for 3 particles. If you can make it in less than 15 minutes, give me a note, I would set a record. For 4 particles, it would perhaps take a couple of hours. For 5 particles, a couple of days, and so on. But we have a problem to describe a kind of quantum state of this table. It's impossible. Right, good. So we have normalized, we have symmetrized a function, and from the plenty, we just got one, and that gives us, leads us to important conclusion. One set of occupation numbers just correspond to a single state, unique state, which is properly symmetrized. Good, let us see what do I have to do next. Antisymmetric wave function. It's almost the same, but yeah, eventually the difference is, let me get a small preview. The difference is that we have only 2 occupation numbers, 0 and 1 for fermions. The state is either empty or filled. Right, but kind of the flow is precisely the same. We fix these filling numbers, these occupation numbers. But owing to Pauli principle, I hope everybody understands this, it's either 0 or 1. One cannot make an antisymmetric wave function with, say, 2 particles in the same level. It will be 0. So one state, one fermion. Right. We get all possible wave functions by starting with 1, putting particles to these levels, to the boxes, and then we make permutations. The only trick to do, you change sign anytime you make an odd number of permutations. Say you make permutation 1 and 2, you change sign, it comes as minus. Then next to it you do permutation 1, 2, 3 to 4. This permutation comes with plus. It is a product of 2 permutations. All right, again, we do all possible permutations. We've got this gigantic expression. So here we have plus minus terms. It is funny to note, it was a kind of some interesting discovery that eventually for fermions, although it's a full number of terms, it can be at least written in a compact way. It appears to be Slater determinant, Slater of a person, that one. So we have a matrix with indices, particles, levels. It's a square matrix because there's only 1 particle in the levels. The number of particles, the number of field levels is the same, right? And we make a determinant of this. Let's see how much time I have. Oh, quite a plenty. So let me just do it. Right, so for 2 particles. Matrix, so that would be psi 1 of R1, psi 2 R 2 psi 1 R 2. Aren't you sleeping already? Oh, R1. Good. That's for two particles. Now let us recall. If you cannot recall, there's a little bit of problem with your linear algebra skills. Let us recall what would be determinant of this matrix. All right, I just remember it as a crisscross motion. Diagonal product of these two minus diagonal product of these two. And this is an expression which we already seen, antisymmetric combination of these. Oh, what's going on? Jesus. Oh, just bad connections. Very good. At least it's rational. Right. So that's the way to symmetrize, anti-symmetrize two particles. But whatever, perhaps I've been educated in a very tough country of Soviet Union. So as an exercise, I was given to compute determinants of 3 by 3 matrix. Okay, that was enough for me. All right. If you want to feel pain, try this. Right, it's still awful number of terms one has to deal with. Right, okay, that was antisymmetric wave function. Now let us calculate normalization factor, and it's the same calculation. One has to compute. Let us see, I got to share screen for Zoom. Okay, I hope it's good again. So it's the same number, but one has to now take into account that fill-in numbers, occupation numbers are only 0 or 1. One can apply it here, and fortunately, factorial of 0, factorial of 1, it's just the same, it's 1. Right, that's how we come to this number. Still big number, you know that factorials are big. Yes.
So the occupation numbers are either 0 or 1 because we have variables, right?
Yeah.
But so the k index of the NN state, it represents everything. It includes spin and includes all.
That's right. I did not talk about this, especially, right, sorry, because I need to explain it more detailed. Usual way to do this, if you look at books, you can see this way, is to say, okay, there are plane waves, there is spin, and on them, establishing it as a single particle levels, one starts with quantization. But who cares if particles have spin or not, if they're plane waves or not? So that's why I just took a single particle Hamiltonian. It could contain spin, it could not. It has a certain set of eigenstates, certain state of eigenvalues, and each element of the set I treat as a level. Good, so I'm done with anti-symmetric wave function. Let us see what is in the chat. Okay, there was a question from the chat. It is the same. Let me just get to this. transparency. It is the same for symmetric and asymmetric. That's why I showed this transparency, right? So what is the trick? The trick is to note that if pi is not the same as pi prime, these states are orthogonal, right? So we get only something sensible if pi is precisely pi prime. That's why I rewrite it like this. Yeah, it is not important what permutation, if it changes sign or not. It's not important for this calculation because we sum up squares, right? We sum up squares, so plus minus doesn't matter. Fine, let us see. I guess I was so inspired that I did it too fast. We still have to talk about Fock space. So Fock was a person like many persons which you know in kind of fathers, founders of quantum mechanics, like Heisenberg, Schrödinger, who else? Pauli, who else? Do you know the name of one? Dirac. Yes, Dirac. Heisenberg, or did I say Heisenberg? I know them. Vladimir Fock was in this role, so he was not that famous. He didn't do many spectacular discoveries like the guys did, but he just made one, and we kind of remember him from that. He has formulated the Hilbert space for identical particles. Right? Let us understand first why do we need a new space, right? We've got so many spaces, and these spaces are really spaces. There are so many wave functions. But okay, it looks like we have just opposite task. The spaces of all solutions of Schrödinger equation for a particle. It's too large, and we have to clean up. We have to get rid of all the states which do not satisfy symmetry postulate. Right. So there are several steps to do, and we begin with a space of all solutions of Schrödinger equation at a given n. All right, if we just follow what I did several transparencies before, I would have to get busy with reduction, with throwing away the state. But first, it was kind of a rather instructive idea of Fock. He said, why don't we combine them all? Why don't we combine? Kind of, what the hell is the difference if the system contains 100 particles of 101? Perhaps the system is very close. Perhaps we have to put it to the same space. That's what he did. First, he combined all the spaces, and even he included the vacuum, which would sound crazy to me, but it's very important for quantum field theory, for instance. Now, the state with no particles whatsoever which kind of would consider nothing, garbage in classical physics. It is promoted to a legal quantum state. Includes vacuum. There are plenty of states for N1, N2, and so on. All this combined. That was second step of the construction. And now this reduction. So first we need to understand whether we make this particle for fermions or for bosons. And upon this decision, we rather symmetrize or anti-symmetrize the basis states, as I did several transparencies before. Then there is a kind of time to clean up. We throw away all states that disagree with symmetry postulate. So for each choice of occupation numbers, we end up with a single state. That's what we get is a Fock space. Right. And okay, good physics is compact notations. It's not yet very compact, but I guess it's much shorter than explicitly writing wave function with 1 zillion arguments. Right? This is notation for an element, or in other words, for a basis vector. Remember, it's Hilbert space, and wave function is superposition over basis states in this Hilbert space, right? So this is an element, this is a single basis state. And it is completely defined by a lone row by an infinite set of occupation numbers. For each level, we define occupation number. For fermions, it's 0, 1. For bosons, it's any integer number, including 0. That gives us an element. And again, as I said, vacuum is also an element. It is promoted to the legal quantum state. That's it, we got the space, but we also recognized the difficulty. What are we after? We want to look at the systems of big number of particles, and it should not matter for us much how big this number is. Again, intuitive reasoning tells us there should be no much difference between the system of 100 and 101 particles. And there should be no much difference if you take a state of macroscopic number of particles and just add 1. So n should not matter. But if you look at practical side of calculations, it does matter. Formally, we should, for instance, take plane waves and write down all possible permutations and sum them up just in order to get a single state in box space in coordinate representation. We just cannot do it physically. Actually, on Monday, I will try to give you an attempt doing this physically. Right, we have to proceed in a other way. We need a better picture. We need a better orientation in this basis, in this Fock space, right? And that's how we get to second quantization. It would be logical to start with second quantization right away. I still have like 15 minutes. That's something strange today. I never did this lecture so short. Was it perhaps a lack of questions or whatever, or your favorable reaction? Oh, there's a question, even two. Right, so there was a question, and the question was why psi look, I rewrite it a bit, what I've been talking about. Why is this function oops, wrong place. Let's see. I write it here. So there is one of the functions we consider exchange. We got another one. R2, R1. And the question was why these functions are orthogonal. Who can help me? Yes? Inner product, that's why? That's right. So why this inner product is zero? Right, precisely. This guy is zero because psi1 and psi2 are orthogonal. Why they're orthogonal? Because I've taken single particle Hamiltonian, I've diagonalized it carefully, and in this case, I know that all these states are orthogonal to each other. So I might want to rewrite it. I guess I need a bit more space. Let's see, how can I do this? All right, I just add a space. So let me do this product. That's one wave function. And I see to do a product, I have to take a bra, have to take conjugated. Now another wave function is coming. Let's see, R2. And the last term, don't worry, it won't last long. Right. Integral over R1, R2. Okay, so this is a product of integral dr1 yeah, have to pick up this one times what do I have here? This is 0, each factor is 0 if functions 1 and 2 are orthogonal. So they are orthogonal if I just take these functions from my I wouldn't say what. That doesn't work. But I was careful enough. I first had a Hamiltonian, diagonalize it in this way. I made sure that wave functions of the levels are orthogonal. Good point. I kind of never stressed it during the lecture. Thank you for your question. Fine. If there are no further questions, I guess, yeah, please.
A few slides back, there was symmetric wave function. We said that the wave function can be described by a permutation of the state and they all come with the same wave factor. But then here we have an expression for the wave factor which depends on the occupancy of any K box.
Yeah. First of all, we fix occupation numbers. So we don't take all possible wave functions. We take wave functions which correspond to the same occupation numbers. It's much smaller subset than the whole set. Still, there's a plenty of those. We have a formula for this number, but it's only functions at a fixed occupation numbers. Then we do this symmetrization of anti-symmetrization. From many, we have only one, right? Which means that for each set of occupation numbers, we have found a unique wave function. Yes?
Why do you get zero if you have two particles with an antisymmetric wave function?
Let's try this. Good. So I take level 1 and I load two particles into there. Now I'm gonna permute. I got an alternative. But is it really an alternative? Its blood is the same wave function. Right? If I will try to anti-symmetrize it, I just got 0. If I symmetrize, that's no problem. I just take it twice. It's okay. So two bosons can be in the same level. Two fermions cannot. Or in other way to say the same, this function is already symmetric with respect to exchange. There's nothing to do. Fine. So, if there are no questions, thank you for your attention. So, we will see you. Oh, yes. Say it again.
You can't have both symmetric and asymmetric phasing states in the box space.
I could make, for instance, compound Fock space. I could combine Fock space for electrons and for, let's see, what are bosonic particles, and for photons. That's fine. But within same sort of particles, I have to make a choice. Either they fermions or they bosons. Yes, the question. Yes, I guess I answered. Was there new ones? Oh, yeah. Yes, I guess everybody got this question. I won't formulate it. I mean, for arbitrary choice of energies, the only degeneracy is the choice of filling factors. So, in principle, the occupation numbers. In principle, if you change occupation numbers, you go to other energy. But for instance, one could do tricky things. For instance, one can say that energies of all levels is the same. In that case, one can have larger degeneracy, that's for sure. But for general case, where all energies of all levels are different, it is okay. So the degeneracy is only connected to the choice of different occupation numbers. Does it answer your question? All right. Good. Thank you for the questions. See you next time on Monday.